Hello, everyone. I hope you can all hear me well, and welcome to another Scope workshop. So today's workshop is a little bit different one. We are going to have Dennis with us. So Dennis is going to talk a little bit more about his work. But before I bring Dennis on stage, I want to go and share a couple of interesting things that we've been working on with Scope on this week. So for the last couple of weeks, we are on this consistent pace of shipping a lot of things. And the best place where you can learn everything about what we're currently shipping and be the first one to figure out those things together with us is in our Discord. So if you haven't already joined our Discord, go ahead and do it. This QR code is an invitation for it. We are streaming today on X, on YouTube, on LinkedIn, Instagram, all over the place. And those are the good places to be. But for the immediate connection and collaboration directly with the team and everyone else, I strongly encourage you to join our Discord. That's where we usually post the first things, and you also get the opportunity to contribute to the project even more, chat directly with the team members, and help shape us the project itself, the scope itself. Talking about shaping the scope, one of the awesome parts of this about the scope is the fact that it's a free and open source project. So if you go to this QR code, this is our GitHub repo, where you can see our current code base, you can contribute to it, you can also see a bunch of PRs that are currently open. Sometimes I say people, can get there and also understand and see, what's coming up and what are the next things that we are trying to build. And also, we very much appreciate when people are finding any bugs, issues, or anything that could be quite helpful for us to understand the current situation with Scope, or if you're encountering any issues, or if you want just to share your feedback. Using issues on GitHub repo is one way that you can do that. And as I said, we very much encourage that. While I was preparing for this presentation, I was greeted with this dialogue. That means that literally while I was working on something in Scope, our latest new release 0.2.2 has found its way out. So if you want to get the latest Scope, you can get it from this QR code. This is our 0.2.2 release. Last week, I remember we were at 0.2.0. It was a very interesting release for us because we introduced the graph mode, we introduced the new onboarding flow. With this new release, we are introducing a bunch of new improvements, and some of them are, for example, multi-source and multi-sync. So now workflows can contain multiple sources and sync nodes in a single graph, right? So previously, you've been mostly limited or constrained by just having a single one. Now each source routes to its own input track, each sync shows its own parsing state, and stats. That means frames per second, bitrate, and per node recording also lets you capture each sync individually. Then there is also audio in Node. There is a shift in scope that we are now, even if you go to our GitHub, you will see that we deliberately say that we are talking about the generative AI pipelines, not necessarily just real-time video. And we are very much interested in audio. And previously, the last week, we had our integrations week, and we talked a lot about MIDI, about DMX, OSC, a bunch of different integrations enabling people to connect Scope with their existing tool set, with stuff like Resolume, Touch Designer, and a bunch of other things. So we try to make Scope essential to be an essential part of your workflows and your creative endeavors, whether it's creating music, creating videos, creating interactive installations, or in most cases, what happens is a bunch of those things together. So this is what you get with 0.2.2, which you can download right now. If you're already using our Scope app on the first next, running it, will you'll see that pop up that I just showed you, and you'll be able to update it really quickly. Another thing that we launched this week, as I said, every week is a launch week at Daydream these days, is a code skill for Scope. So what we've observed that, with Scope being open source and freely available, a bunch of people are using coding agents or AI-assisted development or vibe coding, however you want to call it, to develop with or for Scope, right? So already we had our documents that are very LLM friendly, and you can use them through Upstash, MCP, like this Context 7. But now we also went and built this Claude Code skill containing best practices, even some code examples that allows everyone to build more with Scope and faster. So scan this QR code. You can get a link to, this is a link to the repo. You can see how it works. There's also some videos and blog posts around it we believe it's going to be quite helpful for everyone who is trying to build and wants to build with scope. But all this aside, today I have an honor and privilege to bring up to stage Dennis Menn. So Dennis and his team, they've worked on something called training-free latent inter-frame pruning with attention recovery. So to tell us a little bit more, not a little bit more, to actually tell us a lot more about that is Dennis. Dennis, welcome. We can see you. Can you hear us? Hi.
Hi, yes, I can hear you. Thank you very much for inviting me.
Yeah, Dennis, it's awesome to have you with us. We've seen your tweets a while ago, and my colleague Hunter, he noticed like, hey, this person would be very interesting to our community, and we would like to learn a little bit more about your work. And why don't you start by two things? One thing, you can introduce yourself, but other thing, settle a bet for us. Is it LIPAR or LIPAR? How do you want us to pronounce it? Because we were not sure when we were reading the paper.
Thank you very much for inviting me. So basically, you can call it whatever you want because it's synchronous of the latent inter-frame pruning with attention recovery. I call it LIPAR, but you can also call it LIPAR. Both works.
Okay, both work. So okay, whatever works, that's great. Dennis, tell us a bit more about yourself. So you're currently a PhD student at the University of Texas at Austin, right?
Yes.
What's primary domain of your research and work, and what led you to LIPAR or LIPAR? And then you can walk us through it and tell us a bit more about it.
Sure. So I'm a PhD student in UT Austin, advised by Professor Dana Markulescu, and one of the senior lab mates is Jeff Liang, the author of Stream V2V. He's also a collaborator of this work. And our lab mainly focused on efficient machine learning, how to accelerate the machine learning pipelines. And some of our lab mates work on large language model, while me and Jeff Liang works in video generation. And my ultimate goal is to see like how fast video generation can be, and whether it can run on a consumer grade GPU to reach real time, which means that 30 FPS. I think this is my ultimate goal.
Mm-hmm. Yeah, and that's exactly intention of your paper and the stuff that you demonstrated there. And when we say consumer hardware here, we're talking like 4090s, 5090s, but you did great stuff at 4090s. Okay, without further ado, do you want to bring your presentation up, share your screen? I'll put it on the stage, and you can walk us through your work. And in the meantime, I put up this QR code above for everyone on Discord to ask questions. Also, folks, if you want to ask questions on any of the platforms that you're streaming at, just type some comments. Dennis will do his best to answer it. I'll be happy also to bring them on stage. So feel free to engage, and after Dennis has shared his presentation, he'll go and answer a bunch of those questions. So if you want to just share your presentation screen, and I will bring it up or just start it.
Okay, sure. Mm-hmm. So I think I shared the screen.
Yeah, the floor is yours. Go ahead.
Okay, sure. So just to make sure, can you all see my presentation, the slides?
Yeah, we see it. The University of Texas at Austin, beautiful slide. It's up there.
Okay, thank you.
Go ahead.
So the paper title or the project title is actually a training-free latent inter-frame pruning with attention recovery. And we are ENIAC Lab, Energy Aware Computing Research Lab, and I'm advised by Dana Markulescu and collaborate with Professor Zhenfeng Shi. He's the author of Stream Diffusion. And the main contribution of our project is we can actually reach 20 FPS for real-time video editing on a single 1490 GPU without additional training. And our settings is 1.3B self-forcing model, 4-step denoising, and FP16 as data type. And I can briefly demonstrate what we have achieved. And this is the screen recording of the real-time video editing. It still have some delay, but I can see that we are heading toward the step of real-time editing. And basically, you can change the text prompt, and the edited results will change according to your prompt. Okay. And the motivation of our work is we all know that videos contains high temporal and spatial redundancy. And in traditional video processing, researchers save computes and memory by not reprocessing similar patches in pixel space. For example, there's MPEG, JPEG. And the question we want to ask is, can we adapt this concept to the modern video generation pipeline, which is a latent diffusion model, to save computes? And our research pipeline will be, we first verify that redundancy exists in the latent space, because it is very obvious that pixel space has redundancy because you can see it. But is this still the truth in latent space? The second part is we actually design a framework called Latent Inter-frame Pruning to fit the pruning method or the conversion method directly into the latent diffusion model. But we found that this does not work well because there will be a train-inference discrepancy which will incur artifacts. So we proposed a tension recovery mechanism to close this gap. And finally, combining latent inter-frame pruning with attention recovery, we get the final workflow, which is latent inter-frame pruning with attention recovery, LIPAR or LIPAR, but both are fine. And let's start with the first questions. Does redundancy exist in the latent space? And just for a brief introduction, latent space are obtained by pixels encoded by CNN, FFN, P4 network, and self-attention layers. Because it passed through self-attention layer, it becomes not so straightforward whether the local information is still reside in the local in that patches, or it will spread to the entire global patches. Because self-attention calculates attention throughout the entire pixels. So the first thing we do is we calculate the Pearson correlation between the changes of pixel patches and the corresponding latent patches. The reason why we do so is if there's a strong Pearson correlation, it means a strong linear relationship. This means that if patches does not change, because here we measure the changes of pixel patches in the same spatial location. If this strong correlation exists, it means that if pixel does not change, then your latent patch also does not change. But what this does not change means, basically it represents redundancy. Because, pixel does not change, means you have a lot of identical patches. Then why bother re-editing it or retransmit it? And the result is actually quite astonishing. We evaluated two variational autoencoder on one 2.1 and one 2.2. The architecture is actually different for the two architecture. And we evaluated on the entire Davis train validation set, and we got 0.69 and 0.77 for the above quantity, which translates into strong linear relationship. Okay, so after knowing that indeed the changes of pixel space can transfer into the changes in latent space, the next question we want to ask is decoder sensitive to compression error. And what we mean by compression error here is we will substitute the latent patch in current frame with previous patch if the difference, which measured in L1, is small. For the video in the left-hand side, we do not compress it at all. And for the video in the right-hand side, we compress 34% of patches, which means that you reuse previous latents by 35%. And the reason why we call this compression is because if you can substitute latent patch with previous latent patch, it means that you do not have to spend the same computes on two identical patch. You can throw the duplicated patch away just to edit it. So we call it compression. And you can see the result actually looks pretty good. Even after you compress it by 34%, you do not see a huge difference between the uncompressed results. And combining the experimental results we obtained from those two observations, I think the implications are: the first, redundancy indeed exists in the latent space. And the second is the decoder is insensitive to the compression error. This motivates us to explore further because these are ideal properties that we can directly transfer the compression algorithms in pixel space to latent space to save computes. But the difference is, in pixel space, you do not retransmit or reprocess the duplicate patches, whereas in latent diffusion model, you do not re-edit or regenerate. And let me first briefly introduce the LIPAR framework. LIPAR actually contains 3 steps, but before I dive into those 3 steps, let me first briefly explain how latent diffusion model works in video editing. So given you have a source video, you will pass it through encoder to encode it into latent space. The goal for this is you want to shrink the dimension of the input videos to save computes. But this is a fixed dimension latence for all videos. And you will pass it through the diffusion transformer to denoise. Then you obtain a denoised or edited result, and you send it in to the decoder. And you will decode it and obtain an edited videos. And what we do essentially is we first apply latent inter-frame pruning. The idea is actually quite naive. If the 2 patches in latent space are similar, I mean, the 2 patches has the same spatial location, but adjacent in time stack or in frames. If they are very similar, then we prune it. We only send in DIT the different part to save computes. And the third step, what we do is we have to restore the dimension of the edited latents. The reason is decoder requires fixed dimension latents to decode. So if you prune it, then there will be a dimension mismatch. But how we restore the latence dimension? We copied patches from denoised latents. The position is same as where you prune it. But this actually does not work. You have to add a very critical step called attention recovery to mitigate the train-inference difference. And latent inter-frame pruning is actually much harder than you see as this formula shows. It actually have a lot of complicated interning steps in reality. Okay, so a question to ask here is, why is there a speedup? The speedup mainly lies in because you shrink the input dimension of latents. This translates to fewer tokens. Fewer tokens translate into fewer computes for diffusion transformer, and where diffusion transformer is the main computing bottleneck for the entire pipeline. Okay, so naively applying latent inter-frame pruning and restoration will actually result in artifacts. So for the video in the left, this is the input video, whereas for the video in the right, this is the edited results. And the problem is actually quirky. You can see artifacts occurs here, here, and here. And I think a critical question to ask is why artifacts occur. And I can pause for 20 seconds or 30 seconds. You can guess like why artifacts occur. It is perfectly fine if you did not guess it right, because we take something like a month to figure out what exactly is going on.
So you're giving our community 30 seconds to try to answer that. And you gave yourself a month. That seems fair. I have high expectations of our community, but joking aside, there was someone saying, does it has to do something with the training data? Is it related to the training data?
Yes, it is related to training data. That's a very clever guess.
Mm-hmm. That's from Jambri, from our Discord, one of our original Discord community members. Yeah.
Yes, I think I should discuss with you when I'm developing this method. It will save a lot of time.
Also, Optic Mystic, he says, I'll bring it here. Could it be replicating artifacts from the video compression itself? Could that also be one of the reasons why these artifacts occur?
That's a very great question. So when I present in our group, in our lab group, also some of my lab mates ask whether this is a potential reason. But actually, I don't think so. The reason why I don't think so is we already tested in this step. After you decompress it, there's no obvious artifacts. So likely it is caused by DIT, diffusion transformer. To be simpler, to put it simpler is for the compression experiment, compression and decompressing experiment, what we essentially do is we do not pass it through DIT. And we directly restore it by copying it. By doing so, we do not observe artifacts. So artifacts is likely a cost from DIT, not from the compression itself. Okay, so I think one of the audience answered very correctly. It is caused by train-inference misalignment, because you can imagine when we are training, we use patches that is unpruned. So in this case, you have x1 to x6, but now you are pruning it. So x2, x3, x5 are all disappeared. So your input is different than what the model is trained on. The question is, what is the solution? And the solution is actually also quite straightforward. You want the output of the token in the pruned version to be as close as to the full unpruned latents. But how do we achieve this? we can actually slightly simplify the questions. DIT, diffusion transformer, actually consists of multiple repeated attention blocks instead of directly achieving the final end goal. Let's first approximate one attention block first. So this is the final end goal, but let's first approximate in a single attention block. It's easier. And the next question is, can we further simplify the question? So you can actually separate one attention block into 3 layers: self-attention layer, cross-attention layer, and feed-forward network. And I would say feed-forward network and cross-attention is likely not the cause, because FFN and cross-attention operates token-wise. So whether the presence of other tokens does not influence the output of the input token. That is to say, the root cause lies in self-attention. So our goal now simplified into approximating the pruned version, the output of self-attention layer from the pruned layer, from the pruned latent to the unpruned latent. Okay, so this is called attention recovery. And the goal, as I mentioned before, is we want to use capped token to approximate the influence of pruned tokens. So in this case, we have x1 capped, x2 and x3 pruned. And this approximation can be separated into 2 components: signal approximation and noise distribution approximation. And for signal approximation, we propose a solution called M-degree approximation. And for the noise distribution approximation, we propose a technique called noise-aware duplication. And for the M-degree approximation, what we essentially do is we first calculate what is the output value of the unpruned latents, unpruned latents. What you will get is you will get this formula. And in this case, we only demonstrate the influence of x1, x2, and x3. And if you consider rope, the effect of rope and softmax, you can expand the formula into this term, with Ke correspond to Xe, K2 correspond to X2, K3 correspond to X3. Because how we prune the tokens, we prune X2 and X3 only when X1 is roughly equal to X2 and roughly equal to X3. So we can actually approximate this term by substituting X2 with X1, X3 to X1, and form this formula. So we essentially can aggregate this term. And we also have the same term in the denominator. And this term is actually called a log sum exponential. To approximate this term circled by red rectangle, you can directly calculate only the m largest terms. And the m largest term can actually be determined by the position between Q transpose and K, because when you are rotating it, you are essentially shrinking the exponent's term. So instead of calculating the full attention, you only have to calculate the m terms. This is where the memory saving comes from. But you can ask, where does the acceleration come from? I will say, oh, okay. So you might want to think about it. Where does the acceleration mainly come from? It's actually coming from you are generating fewer tokens. Because in the original case, you are generating 6 tokens. Now you are only generating 3 tokens. And this reduction of tokens is passed throughout the entire layers. So you can expect the throughput increase by the reciprocal of the token percentage you pruned. Okay, so after explaining the m degree approximation, let's explain how we can approximate the noise distribution. And directly copying tokens, because now we assume x1 is roughly equal to x2 and is roughly equal to x3. In the signal aspect, this is correct, but in the noise aspect, this is incorrect, because diffusion model by default has IID noise added on different tokens. If you assume they are the same, then you will get a very different distribution compared with they are different. And this will actually cause a huge deviation in attention calculation. We did see that.
Dennis, before you proceed, if I can bring up a couple of questions that are related to this from the community right now. So Jambi says, if I understand this correctly, you're basically avoiding generating new frames as you are using the previous frame pixels that don't move. So you're only creating the new pixels that have shift, right? You're just dropping them and then painting the difference or the movement. Is that the correct mental model to think about this?
In general, I would say yes. So the core idea is if the latent patch does not change, you do not re-edit it, you reuse it to save computes. So that's a core idea. But naively applying this method does not work, will result in artifacts. The reason is the attention recovery mechanism. Yes.
Okay.
So I would say the audience idea is correct.
Yeah. And the other, almost like a follow-up to this one from Optic Mystic is, so the latents that are pruned are the ones, let me bring that actually on the stage. So the latents that are pruned are the ones that are redundant. Does that mean it's sort of like caching it? So, but that's the essence of your attention recovery, right? It's not really at caching it in the naive way that it was there before. It was more about this attention recovery approach that you're employing here, or is it a bit different than that?
Yes, you are correct. We are not actually caching it. We do not calculate it. So okay. We do not. Yes. Great questions.
Yeah. Okay. Go ahead. So sorry for interrupting, but they were really timely to this, so I wanted to bring them on the stage. You can go ahead.
Yeah. Thanks. Thank you very much for bringing those questions. I think these questions help clarify. So actually, direct duplicating does not work. You have to filter out noise or use tokens without noise. Either way will do. So you will avoid this noise distribution mismatch issue. And in our attention recovery, we directly use tokens without noise from KV cache, because KV cache in self-forcing model, they are clean, they do not have noise. And this is the full implementation. I will not jump into it. And if you are interested, you can see the paper. But the main idea, I already explained it. Okay. So I will first show the qualitative comparison on edited videos. And for the videos in the left-hand side, it's the direct output of self-forcing model. And for the videos in the right-hand side, it is the output from LIPAR. So it's a self-forcing model plus latent inter-frame pruning with attention recovery. And when I'm playing the videos, the frame rate are the same. And the frame rate here indicates in the actual generation, what is the frames you generated divided by the denoising time. So when seeing it, you will not see it become faster. But when you really generate it, you will see it become faster. And the red word is the prompt. But I did not show you the input video. This is actually me. So you will not see a performance degradation, but you do see a very obvious speed up. And we actually further conduct a quantitative comparisons. We evaluated our method on 51 video prompt pairs on David's dataset with 14 human raters. And we generate all of the result using an A6000 GPUs. Later, I did use 4090, but for this experiment, I used A6000. It's actually slower than 4090 in terms of inference. And quality-wise, we compare with self-forcing model, stream V2V, stream diffusion, control video. And the deep green means ours wins. The light green means draw. Human participant cannot decide which one is better. And the original means the baseline wins. And our method is slightly more preferred compared with the baseline. The reason is our method actually enhanced the background consistency when generation. So you can see that in the left-hand side, the background of the video will actually change, whereas ours will not, because we use the latent inter-frame pruning. And our method wins control video by 84.9% and stream V2V, stream diffusion by over 90%. And as for the throughputs, compared with the original self-forcing model, we can improve roughly 1.45x on the 51 video prompt pairs, and roughly 2x on conferencing. Because when you are conferencing, the background doesn't change, and you only counter for a very small portion in the entire screen or frames. And we later tested on 1490, and we found that we can reach 20 FPS, as I demonstrated in the beginning of the presentation. And we also have, it's 29%, not 20, 29% of memory reduction in GPU peak memory usage. Okay, so the conclusion of our work is we first observe a strong correlation between the changes in pixel space and the changes in latent space. And we design LIPAR, latent inter-frame pruning, with attention recovery, the first framework that adapts video compression algorithms in pixel space to the latent diffusion model. And we also propose attention recovery, a condition that pruning should satisfy to preserve the model performance. I did not test whether it is a general condition, but I do believe it is a general condition that it is you have to satisfy when you are pruning in the transformer architecture. Because when we are deriving those things, we did not use the prior knowledge of whether this is video generation or LLM. Okay, so this concludes my presentation. Thank you very much for your attention, and I am happy to take any question.
Dennis, thank you so much for this. This is awesome. And we do actually have quite a bit of questions from the community that I want to bring up on stage. So there is a one. Give me 1 second. Which intuitively I think it makes a lot of sense. So the question is, so if it's a more dynamic video with much more changing on screen, is there a less potential latence that can be pruned because of the movement and less of the area that is staying static? Is that a fair assumption?
Yes, that is 100% true. But the lower bound, I mean, the worst result you can get is the baseline because you just don't prune anything. But if your camera moves a lot, then likely you do not have a lot of pixels that you can save. But maybe, I mean, I did think about this before. I think maybe it can still be achieved because when you are moving the camera, I would say like for the pixel that is originally in this part, it may move to this part, right? It does not disappear. So maybe through optical flow, you can correct the position, and perhaps you can still save some compute, but it's actually not that easy to implement. So you're right. So when you are moving the camera position, for my latent inter-frame pruning algorithm, you have fewer things to save. But you may be able to compensate it using the optical flow to correct the camera movements.
Okay, so when talking about this limitation around the camera motion, right? When the whole frame is changing, there's less to prune, as we established. So let's say in the real-time video editing use case, you kind of hinted at that, right? Would the hybrid approach be one where you combine LIPAR with something that's more like optical flow aware wrapping to handle the camera pans? Is that the hybrid approach that would be interesting to try out down the road, maybe?
Yes, that definitely. I think integrating optical flow to adjust the camera movement is definitely a research direction. But I would not expect it to be training free. Perhaps you need to have some training elements inside. Yes, because when the camera movement is moving, it at the same time it also look at new things from a new angle. So you may not be directly able to substitute it. Maybe you can spend less compute, but you might still need to edit it a bit.
Gotcha.
That is my guess.
Seems reasonable, and I mean, I love how audience is engaging with these kinds of conversations. So there's another question: have you done any testing with a physical zoom? Like the perspective in that case would still shift slightly. How would that affect it? Have you experimented anything along those lines?
So I would say this one is actually quite similar to zoom, because in zoom you have a fixed camera position, and based on the fixed camera position, you added the video real time. Yes,
you meant
so
more like a field of view zoom, right? Like a FOV zoom, right?
Sorry.
So the follow-up comment here from Jambri was that it's more like a FOV zoom, like a field of view zoom mechanism here.
So I think the critical point is whether the camera moves. When you are doing the zoom, usually camera does not move that often. So in this case, LIPAR works quite well.
And I mean, his thinking is like if camera gets closer to you, right, then the perspective shifts, and that inadvertently that definitely affects more of the frame itself, right? So that is, yeah, I see that he's bringing that up. Would LIPAR work well in those cases as well?
You mean like if I move closer to the camera?
Yeah, you could literally perceive it like that, exactly, because the perspective would shift, right? So still a bunch of pixels would change from frame to frame in that aspect.
So if you move closer to the camera, I would say LIPAR still works well, because you can imagine you are moving, but the background stays the same. So if the background
Gotcha.
is still, when you are moving it, the background is still still. But if you are moving the entire camera, then the whole scene change. Then you do not have a lot of things to save without the aid of optical flow.
Yeah, fair point. Um, I want to take a step back, right? So your paper draws a direct line from what you would generally call like a classical video codecs, like age 264 to 65, into latent diffusion. So at what point in your research did you have this moment like, hey, wait, nobody's done this before? And what made you confident that this temporal redundancy would survive the encoding into the latent space? Was there like a specific model moment when that happened, that like a sense of knowing that okay, this could work, or it was something that you did in a previous research and that just materialized in this point at this point?
That's an excellent question. So to answer your second question, we know it might work after we perform these experiments, these two
Mm-hmm.
experiments. So we calculate the correlation of the changes in pixels versus the changes in latence. We found there's a strong linear correlation. So this means that if the pixel in a patch is still, it translates to a still patch. Also, we found the decoder is insensitive to compression error, which means that the result is basically the same if you switch the current patch with the previous one. Combining these two properties, we know latence has some properties that is similar to pixels, that is critical for adapting the video compression algorithms. And for your first questions, like how do we know no one? I mean, we are the first to work in this part. That's actually a tricky question because you can imagine at the same time there are something like 10,000 papers
Yeah.
being written in a year that is related to machine learning. But why we believe this is the first work is first we search it, and we have collaborators that are experts in this field, Chen Feng, Jeff Liang, advisors. And third, we propose this. We think about come up with this idea soon after self-forcing is released. So at the time, we know that the information we gather is probably the newest. Yes.
Nice.
And,
Yeah, but well, and you said it right. I mean, that there's a bunch of papers being published, and as a part of the scientific approach and method, you always do the comparison and literature review to figure it out. But one of the things that personally for me stood out is this entire attention recovery. I think that's where the most of the real intellectual heavy lifting is happening, right? So you're essentially almost like faking out the self-attention mechanism, so it doesn't notice that patches are missing, right? So could you walk us through the intuition of why you split the approximation into signal component and the noise component that you mentioned in your paper? Was there
sure.
again like a moment where that happened, or what induced that separation?
Sure. Thank you very much for bringing this up. So for the diff pruning and the restoration, it took me something like 1 or 2 months. But for the attention recovery, it takes me 4 months. So much longer than
Yeah.
the diff pruning and restoration, much harder. And why we know we have to separate signal approximation versus noise distribution is, first of all, initially we did not separate it, and we got very bad results. So we know something went wrong. So this is what you will achieve if you do not separate it. You actually get a very noisy wrinkles and patterns. So
Okay.
yes.
You get a very obvious hint why you should be doing a separation. Like I thought it was more like an intuitive thing, but you already did an experiment that's driven into that direction, and basically, directed the rest of the research towards that. That's pretty
Yes.
awesome. One other thing that I want to ask you, I know that you're running on time, but this is incredibly impressive research, and we have a bunch of questions. The memory reduction, right? At some point you mentioned it going from, what was it, 20.7 gigs to 16.6 gigs on a 4090, something like that, is,
Yes.
to me personally, almost as interesting as the speed gain for the creator or hobbyist audience. So was the memory optimization an explicit design goal, or was it like a happy side effect of processing fewer tokens? How did you approach it when working around it?
That's a great question. It's a direct consequence of M-degree approximation, because
Okay.
you can imagine when generating tokens, I mean, the tokens that is closer has play a much bigger role.
Mm-hmm.
So you actually do not need to bother tokens that is further away. So when you are disregarding this, when you are throwing away those tokens, you get speed up at the same time. You get memory reduction.
Yeah.
We found it in the equation, but it turned out to be quite straightforward.
Okay. I mean, that's one of the practical things right now. And now, as I'm wrapping this up, let's stay a little bit more on the practical domain. So if someone in our community wanted to take LIPAR and integrate it into their own real-time pipeline today, either as a workflow or a node in scope, or on their own, what would be your honest advice about the current state of the code? Like, what works well? Where are some sharp or rough edges? Because there's also a GitHub repo. You guys shared a bunch of these things. What would you advise to them as practitioners or community or builders who would be interested in bringing something like this into their workflow?
Yes. Okay. So that's again another very great question. This one, what I'm showing is called Streaming LIPAR. We do
Okay.
not
Yeah.
use the L1 norm calculation.
Mm-hmm.
Where's the L1 norm? Here, we do not use this threshold. Instead, we use a very lightweight, several KB, I guess, human detection,
Mm-hmm.
a CN human detection to detect human. And we do not send in the background. We only send in the background for the first frame, but we send in the human
Okay.
for the subsequent frames. And this works well when the camera movement is fixed. If the camera position is changing, sometimes you will get a floating hands or things like that.
Okay.
To solve it, you actually need to detect whether the camera has changed. If camera is changing, the position of the camera is changing, you have to refresh it. So you actually need to add an additional mechanism to detect whether the camera motion is changing.
Got it.
And you can actually integrate it with the original LIPAR detection threshold. But we found it by directly detecting human, you get a much higher speed up and more accurate location of the human.
Got it. My last question, then this was also one of the interesting parts. You had it on that slide when you showed preferences, between the LIPAR and human subjects. If you can maybe bring that slide up a little bit more, like your human, yeah, that one. So your human study seems to favor LIPAR over self-forcing baseline. Would you argue that this suggests the current video diffusion systems are sometimes over-editing the static regions, or accidentally including flicker? How do you explain this bias almost in a way that's visible there?
Yes, so I can directly show you an example.
Mm-hmm.
So in the left-hand side, this is the
Yeah.
self-forcing, whereas the right-hand side is LIPAR. So
Yeah.
you can see, even if the background does not change, self-forcing sometimes will incur a fluctuation of the background changes,
Yeah.
but LIPAR does not. And this can for self-forcing, I believe this can actually be removed if you train the self-forcing model well. That it learns if the background does not change. You also do not need to edit it. You do not need to change it. But to answer your question, yes, I do believe it may not be the correct route that you spend equal computes on every patches.
Yeah, kind of makes sense.
Yes.
Us, thank you very much for this. As I said, and thanks to everyone from our community who joined. We had at one point more than 30 people simultaneously watching this and asking questions, which is really, really nice. Dennis, my question for you, a little bit more on a personal level. What's next for you in terms of research, and what are the next steps that you're looking to work on? We would love to have you as a part of our community, possibly build something like this together with us in the community, in the scope. But you being in a PhD track, what's next for you? Tell us a little bit more about that.
Thank you, but right now I cannot tell you what is my next project. I have to keep it
fair enough. Okay, well,
but I'll definitely let you know when I completed the project.
That sounds good, and I will take you on that one. So once you're done with that, and if it's related to real-time video, diffusion models, and these technologies, I would love to have you as our guest once again. In any case, on behalf of the entire community and Daydream team, we wish you a lot of luck in your research and the future stuff that you and the entire team are working on. This has been awesome. Really enjoyed it thoroughly. I think intellectually and from the practitioner point of view, the stuff that you've built was really amazing to see. Thank you so much for joining us. Thank you to our community members and everyone who also joined this amazing workshop with Dennis that we had today. And we will see you in the next one. Have a great rest of the week. Take care, everyone.
Thank you very much for inviting me. I really appreciate it. Thank you very much. Also, thank the audience for attending this. Thank you very much. Those questions are excellent. Thank you.
Yeah, they were really great questions. Goodbye. Thank you, Dennis. Take care.
Thank you. Bye-bye.